worksheet. We're going on worksheet 4. So the idea is to do the rest of the worksheet as much as we can. So it's going to be right. We have done more or less until number 6 last time. The few in the middle that we didn't do, just ask me if you want. If they are more theoretical, but it should be alright. And then there is the number 7 in that worksheet, which is very similar to the question that I asked at the end of the Moodle class. So I assume that you know how to do that. So we're not going to correct it now, unless you really insist. But I'm available anytime on talk if you want to send me your drafts or things like this, right? So let's do number 8. Let me just share that. Right. Okay, so number 8. So exercise 8, we have a linear subspace in R4 that is defined by 2 Cartesian equations. Well, and we will want to find the matrix of the orthogonal projection on the right and find the distance of any item in R4. Who wants to do that? Okay, first question should be quite easy because it's really related to anything we did during semester 3. And let's see, we have, so we have a linear space in R4 defined by items x, y, z, t, x 0. Right, and first question, find an orthonormal basis. Of F. Yeah. Yeah, sure. Yeah.
Okay, so first I think we should prove that the equations are linearly independent.
No, why?
In order to do the basis, because and find the spanning, the span of the. That's how I do that.
Well, how do you prove equations are independent?
That's my point. Just a subtraction, and well, I don't know exactly how to prove it, but I think.
Okay, all right. Equations are not independent, or dependent or independent. Equations are equations, so it's how we define our space. What we need we need independent vectors.
Yeah.
For the space, right? So we need to find the spanning vectors.
Okay. So I do it with the reduced echelon matrix.
Why not?
That's how I do it.
Yeah, very good.
So I have I have 4 pivots, which is.
Show me the pivots.
I don't have any pivots.
Oh yes, you do. What are the pivots?
But that's all the 1, 0, 0, 1, 1, 0, 0.
The pivots are the non-zero number at the beginning of each line. So you have two
Okay,
rows,
so
you
only
can't
two
have more than
pivots.
2 pivots.
Okay, so I fix 2.
Yep. Enough. Okay. Okay, that's correct. The more usual way to do it, okay, is actually the contrary. You can just be a bit on the side. Your pivots, these are the numbers that are at the beginning of the rows. Okay, so they are going to correspond to the dependent variables. So that's the first 2 rows, the first 2 columns. So that's going to be the x and the y. Usually this is how we fix our dependent and free variables. Okay, dependent are the one corresponding to pivots, and the free are the other ones. Okay, so if that's the x, y, z, and t, x and y are going to be dependent and free z and t. So usually this is how you need the contrary. Yeah. It's all right, it works, right? But if you just want to do a systematic thing, that's how we proceed usually, right?
So z is equal to z, t is equal to t.
Yeah.
And then, okay.
But in the end, it works, right? But a more systematic way is to really systematically use your pivots as dependent variables, and your free variables, your free parameter, are the ones that are not the pivots. The other ones. Okay.
And so then I do the span. And so the basis, I should be normalizing the 2 vectors.
Mm-hmm.
So it's 1 square root of 2 of
So that's normal. Is that orthogonal?
Well, I should do the dot product.
Yeah.
So I can do it with this one.
You can give them some names, maybe it's going to make it easier.
Yes.
Okay. Okay, in our case it works. It's going to be, we have naturally some orthogonal vector, and we have already normalized them, so we have an orthonormal basis. If we didn't have orthogonal vectors, we would need to apply the Gram-Schmidt process in order to orthogonalize the basis, right?
Thank you.
Do you want to do the next?
I'm not sure about that.
Yeah, that's fine. Yeah? Okay. So who wants to do the next one? So very good. That's the orthogonal basis, orthonormal basis. Right, so I'm right. Yeah. So let me just sum that up here. We've got F is actually the span of, so you call them U and V. It's more traditional to call them with numbers so that we know, well, like E1, E2. Anyway, that works. So let me just write 1 over square root of 2. Okay. Right, any question on that? Right. Next question is just the matrix of the orthogonal projection on F, right? In the canonical basis of R4. So it's, what should we do? So if you could answer, and I think nearly everyone answered the question on the Moodle lesson. So for that, you needed to do the matrix of a projection. You needed even to go further than that. Right? Here it's just, we've got an orthonormal basis and we need to find the matrix of the projection. Etienne, come to the board. What? Come to. Okay, nobody should use actually computers or phones during class. I mean, don't get used to every time you don't remember something, just check it. No, every time you don't remember something, try to check it in your memory first, or in your understanding, in your reasoning, right? Otherwise, once you're in a test, what would you do? You have no access to any of these tools, so don't get used too much to just check whenever you want. It's not available all the time. So, matrix of the orthogonal projection. So what's the matrix of a linear map in general?
P.
Yeah, if you like. Right, that's the name. How do we build the matrix?
Le formula with some equals.
It's not really a formula, it's just understanding what we're doing. Okay, forget about the projection. Now, let's say I've got a linear map. I know it does things, right? My linear map does something. How do I do the matrix of my linear map? I'm in O4 and I'm looking at the standard basis, E1, E2, E3, E4. Okay, we have to compute that. And how do we build the matrix then? No, it's the easiest thing. How do we build the matrix of a linear map? We put in columns the image of the basis vectors. So these things, they are going to come as columns of your matrix. How long have we been practicing that? Right, so you take the image of your basis vectors that make the column of the matrix. Right? Now, how do we compute the image of an orthogonal projection when we've got? How do we compute the image of an orthogonal projection when we've got an orthonormal basis? All right. So we want to find the image by the orthogonal projection of these vectors. What are these vectors? They are just the standard basis of all four. Okay, we agree on that? So they are just the 1, 0, 0, 0, 0, 1, 0, 0, etc. Okay? So we need now to find the image of that projection on F of E1. How do you compute that?
Using scalar products?
Yes, we need a scalar product. Okay, that's the lesson we saw yesterday. If you want to express, that's the main result of the lesson, I would say. You've got an orthonormal basis. Let's call it B1, B2, because I've already used the E letters. You're in a space of dimension n. You've got a basis, so it has n items, and let's assume that these are orthogonal. Each of them is orthogonal 2 by 2, and they are norms. Okay, so we have an orthonormal basis, right? We take some x that belongs to E. We've got E is spanned by this thing, right? How do I find the coordinates of any item x in that basis? That's the main formula. You've got x is x times E1 times E1. B1 times B1 plus x times B2, B2, etc. Right? That's the main reason. If you have an orthonormal basis, you just find the coordinates by applying the inner product. It's as simple as that, right? And that works only if your basis is orthonormal, right? What does that mean? Each part corresponds to the projection on one of these axes, of this direction. Okay? So the orthogonal projection on one thing is computed by this. It's this inner product times the vector, right? So if we are projecting on that space, it has two spanning vectors, okay? That were called U and V previously, right? How do I find the projection of anything in O4 on that? I just do the projection x times u plus x times v. That's going to be the projection because I have an orthonormal basis on the space that is spanned by this, right? Okay. So now when we need to make the corresponding matrix, we just need to take the image, but for each vector of the standard basis. Okay? So can you do that?
I'm really not at ease with that.
What?
I'm really not at ease with that. I mean,
Okay.
that's my
What we need, you said we want to take the image. We said we have 4 basis vectors. Okay, E1, E2, E3, E4 is my standard basis of all 4. I want to make the matrix that will contain the image of these vectors by this projection. The image of anything in O4 by this projection is given by this formula, right? So you have to apply to calculate this for x equal E1, E2, and E3, and E4. And put all this in a matrix.
Yeah, I just do that. I just can't.
I'm sure you can. Right? You know how to compute that. That's about clear. So who wants to come and do it? Oh, maybe I can. Can I erase the middle? Yes, of course. So, it's all right. You get everything. Right. So let's try it here because otherwise it won't be. Yeah, I can't show it to you. It's okay. Times B1. Well, okay. If you call them B1 and B2, let's get some names here. B1, B2. Right. Okay. Yeah.
So this is the 2 and E1.
B1 is this one over square root of 2 times. Yeah, and D1 is that. Yeah.
So this x1.
Yep.
Times P1. So x1. X0.
Yes.
0.
Is that okay? Did you get that? Okay, so this is going to be our first column of the matrix. I'm going to keep that on the right. So my first column is going to be 1 over 2, 0, minus 1 over 2, and 0. Okay, so you might say here.
So should I write every step? So
Yeah, you can do it directly. So the 3 times.
minus 1.
Can you just complete? So we get 1 over 2, 0, minus 1 over 2, 0, 1 plus 1 over 2, 0. Okay, so that's it. What does it mean? It means that if you want to compute the projection of anything in O4 on that space, you just have to multiply this by x, y, z, t, or by the components of the item that you have. Okay? Right, that's what it's for. That's what it's used for. Right, and we did all the algebra in class. Why is that working? Because if you have something that is x, y, z, and t, what does it mean actually? It means that it's x times e1 plus y times e2 plus z times e3 plus t times e4. That's what it means to have those coordinates in O4, right? Now, if you want to apply some linear projection, some linear map, whether it's a projection or not, if you want to apply a linear map to this, it's going to be the linear map applied to that. And if you use linearity, how can we rearrange that? It's just going to be x times p of e1 plus y times p of e2 plus z times p of e3 plus t times p of e4. Right? And this thing, you can rewrite it. Okay? So by the linearity property, when you apply a linear map to anything in your space, it's going to be written, decomposed. It's going to be written like this, right? By the linearity property, whether it's a projection or not. Okay? So, and this thing, the good thing is that you can rewrite this as your matrix equation n times x, y, z, t. Right? That's why it's the whole thing. Why we have that the matrix representation of a linear map is given by the image in columns of the basis items. Right? Okay. So in our case, we did this computation. We found that the image of each of the items of the standard basis were given by these vectors. So we put them in columns of our matrix. That's our projection matrix. Right? Do you have any question? Yeah?
The scalar product is some kind of dot product, right?
Oh, here, yes, it's a dot product. We are in R4, we didn't say anything else. It's the dot product.
So how will we end up with one of the two when we do the scalar product between E1 and B1, for example?
E2 is that one, B1 is that one.
Yeah.
Okay? So 0 times 1 plus 1 times 0 plus 0 times negative 1 plus 0 times 0. Simple dot product.
But for the first one, for B1, it will be 1 over square root of 2.
But it's times B1, so.
So that's 0. Yeah, that's 0 times 1 over square root of 2 times this, so it's 0.
No, I'm talking about P on E1.
Ah, this one?
Yeah.
Alright. That's something that's happening all the time. So B1 is, if I write this, if I write exactly what we were doing that. That's E1. B1 was 1 over square root of 2 times 1, 0, negative 1, 0 times the vector 1 over square root of 2, 1, 0, negative 1, 0. Okay?
I think I got it.
All right? So that's something that's happening every time when you have normed your vector and that you have divided by the norm of your initial vector, like the 1 over square root of 2, because square root of 2 was the norm of our vector. What's happening is that you have, it appears twice. So in the end, you can factor by 1 over the norm square. Okay? With the experience, you will see that this is happening all the time, so you can go a bit faster, but take your time. If you need it, write every piece of it. Right? So we will have the 1, that's why you have the 1 over 2 that comes as a factor every time. Okay? All right. Any more questions about this? So calculate the distance between any elements in R4 and F. Can I erase the middle of the board? Yes? So how do we define distances now that we have a scalar product, an inner product? Well, when we are in R2 or 3, it's just the usual Euclidean distance. Okay, the dot product corresponds to the Euclidean distance and to our usual notion of distances. But in general, the thing about having a well-defined inner product, it allows you to define orthogonality on one hand and to define distances on the other hand. Okay, to say how far are we from something, right? And this is very, very important in many applications. Why? Because if you want to correct some kind of error, for instance, you need to know how far you are from the good result. Okay, you need to be able to define your the magnitude of your error, right? I'm thinking about machine learning applications, for instance. In those applications, we use a lot of different distances because according to the way you calculate your distance, you will get different kinds of solutions, different kinds of approximate solutions. Okay, so if you define different distance, it means most of the time that you have defined different scalar products, different ways of measuring the things, right? That's why we want to have a global theoretical notion of inner product, right? So, this being said, the distance when we have a scalar product is just going to be given by the shortest length, the shortest measure you can do between your item and the other item you're looking for. But in general, when you've got a well-defined inner product, again, it's just going to be given by the orthogonal projection, right? So you can really picture that you've got something in your space, you've got some linear subspace, you want to measure the distance, what do? You do the orthogonal projection on that linear space, and what you want is the magnitude of this, right? The shortest distance between one point and another is always going to be, that's something very natural, the distance between that point and its orthogonal projection on the place you want to go, right? Shortest time. Right, so that's it. So what we want to measure really is x minus p of x. Right? That's going to be, that's a definition, but we can understand it very intuitively. That's going to define the distance between x and f. Okay, so how do we compute that? Yes?
We say that x minus p of x is orthonormal, the vector is orthonormal to the basis we found in the first.
Yeah. You don't have to go that far, but that's true. Yeah, we can redo all this reasoning, but here actually it's very direct. How do you compute Pf of x? Using the matrix.
Okay.
Okay? So what really we want to do is to do the norm of x minus, we call our matrix m times x. That's all. Right? Or in other words, we can also rewrite it, and that maybe should remind you of what you had to answer to in the lesson. That's also the identity matrix times this can be rewritten like this. Okay? If I've got x minus matrix m times x, that's in R4. The product matrix vector belongs to R4, right? This can be rewritten exactly like this. What do we mean here? What's hidden? Not hidden. What's underlying this here? The fact that when you've got an orthogonal projection, so let's say that is the zero of your space, so you know that as we've got vector space 0 belongs to f, so you've got the normal direction, the orthogonal space to that one. You've got that. In general, E is going to be the direct sum of space and its orthogonal complement. That's the orthogonal complement we talked about, right? So when we're doing, what does it mean? It means that any x can be divided into two parts. One part that is going to be the orthogonal projection of x on f, and its other part, which corresponds actually to the orthogonal projection on the orthogonal space, right? Okay? And the good thing is that those two items are going to be orthogonal together, right? If I take this picture to try to imagine what it means, just means that, so this tries to represent something in R3, which is not our problem, but if you were in R3 and your space F was a plane, you've got a plane and you've got the normal vector to the plane that is going to define your third component, right? So when you've got any x in R3, you can divide it into its orthogonal projection on the plane, and its third component would be given by its orthogonal projection to the normal direction to the plane. Right? Okay? And what we when we're calculating the distance, we're really looking at the projection, the orthogonal projection on the orthogonal space to F. Okay? So that's why well, you don't have to do all that reasoning every time. We just, you have to understand that when we're computing distances, like this, okay, so it's really the magnitude of x minus its orthogonal projection, but what it corresponds to its orthogonal projection on the orthogonal space. Right? So that would be, that's what we're looking for, this, the value, the magnitude of this vector, that corresponds to the orthogonal projection on the orthogonal space. Right? So as what it makes, this inner product, the fact that we can define orthogonality makes everything completely square, right? Means that you're projecting, well, what's remaining apart from the projection is really exactly the orthogonal projection on the other direction, right? And everything works perfectly this way. You see, right? So when we're doing that, that's what we want to compute. We can also see that as this, the orthogonal projection on the orthogonal space. Okay, that's yesterday in the Moodle question. You were given a plane equation, right? A vector plane. It has a normal vector. I don't remember which was the question. Was the matrix of the orthogonal projection on the plane. What's easy is to get the matrix of the orthogonal projection on the normal direction. Why? Because it has only one component. Right? So you compute your matrix of the orthogonal projection on the normal line. Right? That's easy because you just have to do one scalar product with the normal vector. And then to get the matrix you are looking for, you had to go to identity minus this matrix. Right? Okay, so if we compute that, well, we can just, if we write identity minus m or x minus, well, either of those works. So that would just be the x, y, z, t minus this times x, y, z, t. What's the vector we get? X minus 1/2 minus 1/2 of z. Second line will be 1/2 of y minus 1/2 of t. Third, negative 1/2 of x plus 1/2 z. And fourth component of this minus 1/2 of y plus 1/2 of t. Okay, and that's giving me some components. So I'm really looking for the norm of x minus 1/2 of x plus 1/2 of x plus 1/2 of z. Get 1/2 x plus t, y plus t. Also have x plus z. And 1/2 y plus t. Okay, so I'm looking for the norm of this vector. Right, so that's the 4 components of my vector. And so it's just going to be the square root of the squares of these. So I get 1/4 x plus z square, and I've got it twice. And 1 plus 1. Okay? Ask me questions if there are things that you don't understand.
For the second row, when doing this difference.
Y minus 1/2 of y, this one, plus minus plus 1/2 of t. So So that's 1/2 y plus t. Okay, so this I obtained by doing this matrix vector product. Okay, and then I compute the norm. I get 1/4 x plus z squared, 1/4 y plus t squared, another 1/4 x plus z squared, so that together they make 1/2. Yes?
So the part with the 1/2 on the right,
Yeah.
it's the minus m, and the part on the left, it's I. And where is the factor of x?
Say it again. Which part? This one?
So like, yeah,
That's m. Yeah.
and then on the left, it's I, or x, y, z, t.
No, that's mx. So that if you compute, that's this thing. Okay. I didn't choose that. We could give you exactly the same thing. I didn't choose that. Okay, so yeah, that's m, that's x. So that's the m we found in the first questions. That's nx in all 4. That's computing the orthogonal projection on x on f. That's what we get. Generic result. Okay, and so we compute the norm of the resulting vector.
I don't get the square root.
It's just a usual norm, Euclidean norm.
But why we didn't say square root two?
Yes.
Okay, so Euclidean norm, it's the square root, we agree on that, of the sum of the squares of the complement. So 1/4 x plus z squared, 1/4 y plus t squared, 1/4 x plus z squared, 1/4 y plus t squared. Just that I will put together the x plus z squared, 1/4 plus 1/4, that's 1/2 of them. Okay? Okay? Right. So that was exercise 8. Let's do quickly exercise 9. That's this generalization of that one. So exercise 9 tells you, so we are in a space in general. We're in a space E. We have been able to define an inner product because it's an inner product space. Okay, and we've got A. So we've got E, it has an inner product. You note it as you like. You've got A that is a vector in E. Vector may, because it's a vector space, so it's just an item in E, whatever E is. We've got some x, any x in A, and we want to express, so A is different from 0. And we define with A, we define D, which is D as what? It's the span of A, okay? So it should be N. Well, anyway, okay, we define a linear subspace of E, which is just spanned by that single vector. Okay? So you can picture that if you are in R2 or in R3, it's going to be a line going through the origin. Right? And we want, you've got your orthogonal complement to D. Okay, so H, sorry, which is going to be the orthogonal complement of D. Remember, the orthogonal of the orthogonal complement is going to be the space itself, right? So we can write it either way, right? And what we want is we want to get the expression in the usual expression of for any x, the distance between x and D, the distance between x and H. So what are we allowed to use? We're allowed to use the normal notation and the scalar product notation, the inner product notation. Okay, so it's exactly what we've done, right? It's just what do you get in general when we've got that. So you can picture, you can picture this in R3, that helps you. In R3, that will give you D is just a line of direction A, and it's orthogonal complement between D. To picture that in R3, so you've got this. You are given a vector in R3. It means you are just given a direction. Let's say this is my vector A. And when we say D is the span of A, it's just going to be the vector line, the line of direction A. Okay, it's a vector line because it has to go through the origin in order to be a well-defined linear space. Okay? Right. So what would be the orthogonal complement to that line? Yes, a plane. Right? It's just going to be a plane that is orthogonal to that line. You've got a line, you can make the orthogonal plane to that line, and it's the one that goes through the origin because it has to be a vector space. So that would be H. Okay. If I tell you that A has components A1, A2, A3. If we are in R3, it has three components. Let's say it's A1, A2, A3. What's the Cartesian equation of the plane? Of that plane that is orthogonal to D?
A1x, A2y plus A3 is
That's the Cartesian equation. What does it say? It tells you I'm taking all the x, y, z that are orthogonal to A1, A2, A3. That's what it means. I'm taking the plane orthogonal to that direction. I want all the x, y, z that are orthogonal to A1, A2, A3. Write this with a dot product, with a scalar product. It means that x xa is equal to 0, it means that you got this Cartesian equation. Okay, that's where the Cartesian equation of the plane comes from. Right? If it's a plane that goes through 0, it just tells you it's all the points that are orthogonal to that direction. And if you don't want it to go to 0, if you don't work in terms of vector space, you just add equal to some constant value to take the to take a plane that it would be parallel to this one, but not going through 0. Okay, that's why plane equations are given like this. Right? That was just to help you picture what's happening. Okay, what kind of things we are looking at. Right? The good thing in R3 is that we can picture it, and as it has 3 dimensions, everything is not completely symmetric. So, well, I mean, one will have 1 dimension, the other has 2 dimensions, so it's a bit clear to see how that works. Okay, so let's go back to the original question. How do I compute the distance between anything and a line? And I've got x, I want the distance between x and my line. Last year, you learned how to do that by a whole bunch of reasoning in R3, right? Or by using a formula, right? We're doing the same thing, but in general. What do we do? So again, it's going to be orthogonal projection, right? Distance between the points on the line, shortest distance, okay? The one that corresponds to the shortest path to go from that point to the line is going to be the orthogonal projection on that line. Right, and what we want, if we want this distance, it's going to be x minus that orthogonal projection, right? So that's okay, that's definition. Same thing if I want to do the orthogonal projection on its orthogonal complement, it's going to be the same idea, right? If I'm looking for the distance x to h, I'm looking for the norm x minus orthogonal projection on h of x. Right? So what do we need? We need to write these. These are definitions. Whatever d and h are, the distance between x and a linear space, it's just x minus the orthogonal projection on that linear space. That's every time. That works every time. Now we want to expand these two formulas, these two definitions, using scalar product, norm of x, norm of a, and the scalar product between the two. Okay, let's take the first one. You've got x. How do you do this? Do projection of x on d, the orthogonal projection of x on d. How do you compute that?
So scalar product
Yeah,
between a and x
yes.
times a.
Yes and no. That would be true if a was of norm 1. We didn't say a had norm 1.
So we normalize it.
Definition of the orthogonal projection. When you've got just a single vector, that's going to be given by this. Right? In R2, in R3, you can go back to the original definition of the dot product, uses the cosine. Right? the orthogonal projection of that point on that line is on with that vector. You use the scalar product to define that, right? Okay, because you want the cosine of that angle, but you multiply by s, right? So that's projection on D of x. Okay, so let's compute that, right? We just need to expand x minus PD of x. Let's make it square because it's easier to work with the squares, knowing that this is given by that. Okay, let's go back to maybe something that I didn't precise today. What's the norm of x? In general, when you've got an inner product,
inner product square. No, the square root of
Yes.
inner product.
square root x, x. Okay? We applied it in the previous exercise with the dot product. Okay, the Euclidean norm. That's why it's called the Euclidean spaces, right? So if you want to compute a norm square is here, you just have to expand the inner product. Somebody to do that? Yes? You can do it here.
So basically expand it as x squared plus minus.
You have to write it.
That and
Okay, if I don't know the formula by heart. So let's find it again. Okay? Just expand it as the inner product of x minus p of x within something.
So I just do linear product of them.
Yeah. You get back to the definition of the norm. Yeah, that's it. Yes, indeed, you've got a formula for that. But if you don't know formulas, like me, try to find them again. Or know how to find them quickly, right? So, norm square, we just expand the inner product. Okay, that was using linearity with respect to the first item, the first input. Now let's use linearity with respect to the second input. Well, if you already put the minus, no.
We suppose there's, well, we don't suppose they are symmetric. Since
Oh yes, as we've got an inner product, it has to be symmetric.
so we can add.
Yeah. Absolutely. That's the formula. Yes, exactly. Yeah, sure.
And so this is simply the norm of x.
Okay, so we already. So I remind you, in the end, we just want these kind of things in the expression. Okay, so we're getting there, right? We've we've got the norm of x. You can leave the middle part as is.
And that as well?
That's going to be also the norm of PD of x. Let's just rewrite it because that's the formula you can write if you know it, right? Right. If you know your formulas, you can directly go there. If you don't, you should be able to redo that quickly. All right? What else do we get? What about x? Orthogonal projection.
We simply replace PD of x by.
Yeah? Yes, sure. You can do that. Yeah.
But
We already know that PD of x is given by this formula. So yes, you can
so in that case, I just replace this by a over a norm, or I replace it by the.
by the whole stuff.
So I have
You've got all these.
so I have an inner product inside an inner product.
Yes? An inner product is just a scalar number. Okay? Just a number. So yes, you erase all this. Yeah. Okay? That one is the same.
Yeah.
So you can substitute that by this thing, the PD of x is again this.
So I substitute that again.
Take the norm of this square.
Sorry.
That's
Okay. Keep it there.
okay. So let's see what we get. Right? Maybe we can work on that first. By linearity, we can put as a factor anything that is a real number.
So a over.
So what is a real number in that expression?
Can it be a over a norm?
No, A is a vector. Norm of A is a real number. This also is a real number.
Okay, so I don't really understand what I have to do in that
Okay,
case.
you've got something here, minus 2x something, let's call that lambda times vector A. What is lambda? Lambda is all the real part here. All this is a real number. Okay, so using the linearity of the scalar product, what does that give you?
I can put that outside.
Yes.
So that's a norm squared, or
So the real number is that one. The
Yes,
A here
what
is a
A?
vector, so it stays inside.
yes.
But yeah, you will have some norm over A square. Wait. This already here,
Yeah, sorry.
okay? And here we've got.
Okay.
Yeah? Okay. Okay. Let's go on. So this slight simplification is just 2 something times itself, right?
So I just put it as the norm.
No, not the norm. It's just the square of the scalar product x with a. Okay. Again, we will be able to simplify that.
You take up the real number.
So, yes, so we're going to do something like this, but again, all that part is just some real value lambda. What do we know about values? If lambda is an R and A is a vector.
Lambda times the norm of the base squared.
Yeah, lambda squared.
Lambda squared.
Yeah, sure. Yes.
And then I can fix now and simplify.
Without the 2.
Sorry.
That's it. Yes, very good. Thanks. Okay, so it's not every step is simple. Start with what you have, lead it until the end. Yes?
Square the minus 2x the product of x and b.
This comes from this one. Okay? Which comes from this one. Okay, so it all relies on one thing that you have to picture is that yes, we can perfectly put an inner product inside of an inner product. Why? Simply because the inner product itself is just a number. So this term that we have here, it's really something like scalar product of x with a times a real number lambda. Okay, so the lambda is that one, the thing that I've circled in green, right? Every time we've got this thing, right? So when we do the scalar product, the inner product, you use linearity, it just comes as lambda times inner product of x with a, right? Just using the linearity of the inner product. It happens that your lambda was itself the scalar product of x with a, so you've got scalar product of x with a to the square. Okay, so that's happening here. And here, same idea. Except that if we go slightly faster, we've got something like norm of lambda times A. In general, it's just going to be absolute value of lambda times norm of A. If you're working with squares, you just get squares everywhere. Okay? That, you can re-expand that completely starting with the inner product. You will get there very soon. Right? Okay? So, I don't think it's too complicated, but it's an interesting one because you just have to use all the properties of the inner product every time. Okay? So, I think it could be useful for you to retry it without any help after the class, today or tomorrow. Just retry to write this, okay? To re-expand that.
And so in the end, it's square root of this.
And so in the end, yes, we have that this first one is really the square root of that. And computed the square. Right. So square root of x2 minus the other one, which I've erased. I tell you it's going to be much faster, the other one. Can I erase the middle part? Yep. Right. Anyway, yeah, try to repeat that. It's really like the long calculations we did in multivariate calculus at the beginning of the year. It's just something that you have to leave, right? To begin the calculation, every step is easy in itself. Just go as far as you can until you reach the final result. Okay, the other one was the distance between x and h, the orthogonal complement. Okay, I'll redo the pictures. So you've got A, well, you've got D, and you've got H. Right, so we know, we calculated the distance between X and D. It was X minus PD of X. Now, the distance between X and H, if I use orthogonal, well, if I use the same thing, it's just going to be what I want to compute is X minus PH of X. All right? That's basic definition. What's the relation between X, PD of X, PH of X?
Plus and equal.
Yeah.
Non, c'est l'autre projection.
X is the sum of those two orthogonal projections because we've got that E is the orthogonal and direct sum of one set plus its orthogonal complement, which happens to be H. Okay? So now if I want to compute the norm of X minus PH of X, X minus PH of X,
It's PD of X. And so it's
exactly. So it's the norm of that, right? So it's the norm of X A A. Okay, so we get as before. So X absolute value of this one divided by norm square of A times norm of A. So we get okay. Right. So I think it's a nice exercise because it has all the ideas we are using in that part of the lesson, right? In that chapter, right? And in a very generic way. Okay, next one. We're just going to talk about how we should solve this one, but the calculations are very long, so I'm just not doing the details. Okay, so up to that point, we did orthogonal projection on spaces of Rn, like Rn, like R4, R3, etc. But we can do that in any linear space where I can put a well-defined inner product. And we have some well-defined inner product in the spaces of polynomials or in the spaces of functions, right? So that's, or in spaces of matrices. So let's extend that to other things. Okay, so you may be wondering, but why do we bother to do that? Actually, it has a very direct application that you will see next year. Okay, I don't know if you heard about Fourier series. There are some very, very useful tools that are used to solve partial differential equations on one side, and that are also used to make bases for any signals. So if you want to work with signal processing for sound, for instance, you will use bases of functions that are sinusoidal functions, sines and cosines, right? For instance, we proved in one of the early chapters that you could make linearly independent functions using the cosine family, cosine of ns. Okay? We could do the same thing with the sine. We can do the same thing with some exponential or with some complex exponential. This is the kind of thing that will allow you to describe any, more or less, any signal. Okay? Any function will be able, if we have enough regularity, we can describe them as sum of trigonometric functions, right? And that is very useful if you want to discretize signals. That's why all the digital music relies on. Okay? If you want to discretize a continuous signal that represents a sound, if you want to represent it and put it on a CD or on a computer, you have to have discrete values. How do you get those discrete values? Because you get the coordinates of your signal in some bases that you know. Your bases will be made out of those trigonometric functions. Okay, that's how we can reconstruct music, for instance. Right? So all these things have a lot of very important applications in everyday life. Okay, so that's not anecdotal. Right. So the next one, we're working in R of X space of polynomials. The first question is prove that so I've got two polynomial functions and I can define an inner product by saying it's going to be this value. Okay, the integral of the product. First question, show that it's a well-defined inner product. What should we show?
That this is symmetric.
Thomas? What should we show? I think you should really get rid of this computer and phone when you're in class. So, what's here? So if we want to show that it's a well-defined inner product, symmetry,
And bilinearity.
bilinearity. If we have symmetric and linearity, then we get bilinearity. And finally,
Positive.
I'm happy that at least someone knows the lesson. Yeah? Yes, and positive definite. Okay? Symmetry? No problem. Okay? The integral of f times 3 is the same thing as the integral of g times f. Right? Linearity. Not much more difficult. Okay, so for symmetry, if I do the other order of the inputs, it's just the same thing. Okay, so we get symmetric. Usually it's tricky. Linearity. What do? Take two items, make a linear combination. So lambda f1 plus f2, inner product with g, and I get lambda f1 plus f2. I just begin by writing the definition. Okay? That's what it means to take the inner product of this linear combination with g, and then we expand that using the properties of the integral. Okay? That is going to be lambda f1 of t plus same integral with f2. Okay? What did I use here? The properties of the integral. Right? And so this is exactly, and finally, we have to reinterpret that to show linearity. That's really lambda, inner product of f1 plus g, f1 and g, plus inner product of f2 and g. So I've got linearity. Okay? Symmetric plus linearity gives me bilinearity. Okay? These two steps usually are very fast. Okay, the hardest will be on the last one. Show that it's positive definite. So show that it's positive definite. Put twice the same input and show first of all that it's always positive, and if ever it's equal to 0, it means that you started with a 0 item. Okay, so what we do? Plug f with itself, because that's what we're going to use to define norm. Okay, and we know that it should be the square root of this, so it has to be positive, otherwise I can't define a norm. So that will be f squared. What do we use to show that it's always positive? Positivity of the integral. Integral of a positive function is just a positive value. Why? Because we can always get back to the definition, to the geometric definition of the integral. Right? That's just the area below the curve. If your curve, the side area below the curve, between the curve and the axis. If your curve is always above the axis, it's really the area. The area is positive. Okay? But the rigorous justification is by positivity of the integral. Okay? It's very similarly. If this is equal to 0, then if that is equal to 0 and f and the function inside is positive, okay? Same justification, positivity of the integral, it means that your function is equal to 0. Okay, if it's continuous, it has to be equal to 0 for all t. So if the square is equal to 0, it means that f of t is equal to 0. Okay, so we have done that in one of the videos because that's what's called the L2 norm. It's a very, very common norm for signals in general French sense. Okay? That's one of the things that will. The good thing with that is that it's very close to the Euclidean norm, and it allows us to work in spaces of functions exactly as we do in spaces of R3 or 4, etc. So anything Fourier, if you heard that name, you will hear it a lot next year, relies on this also, on this norm. Okay, so we've got a well-defined inner product, and so we can define orthonormal basis. Okay, so the idea here is that we're going to work in R2 of X, a subspace of that. And we want to define an orthonormal basis of R2 of X. So what can we do? We know a basis of R2 of X. What is that?
1 x x squared.
Yeah, standard basis. Never know if it's a T or a T. It's right in between T and T. Standard basis of R2 of X, 1x xt. Okay? Any polynomial of degree at most 2 will be a linear combination of 1, constant function 1, function x, and function x squared. Right? So that's the standard basis of R2 of X. Maybe if we are lucky, it's already going to be orthogonal, orthonormal, orthogonal. Okay? So what should we do in order to get that? If ever it's not orthogonal, what should we do? If ever it's not the case. Okay? So, first, I want E1, E2, and E3. That would be orthonormal, right? So, let's check for 1. Our first one is going to be 1. Okay, so E1 of X is going to be the constant function 1. Should I norm it? Let's see. We begin with a not norm version and then we norm. So let's compute the norm of E1 norm square. What is that given by? Yeah. Okay, that's generate usage of the scalar product, right? E1 prime. That's in our case, let's get back to the definition of our inner product. That's going to be the integral between 0 and 1 of the constant function 1. So 1, right? So it's norm. The norm of this is already 1. So good, we can keep it as is. Okay, we have that. Second one. My second function is x. Maybe if I'm lucky, I'm going to get already something that is orthogonal. What should I check? that
The orthogonal
X and E1 are orthogonal.
with scalar type.
Yeah,
And then
orthogonality is defined by inner product equal to 0. So do we have that inner product of X and E1 equals to 0? Right? So that's, if so, then it's going to be orthogonal. And that's fine. Okay? So, what is that?
on the x square over 2.
So it's going to be the integral, which is very 1, f times g. F is the function that for x gives you x. G is E1. E1 was the constant function 1. dx dt, or, well, you have to write it accordingly, right? So yeah, so that's 1 over 2. 1 over 2 x2 between 0 and 1, that's 1 over 2. Conclusion? Not orthogonal. Right? Right, so we've got, but I can write my E2 prime if I apply the Gram-Schmidt process. Right? Usually, the E2 prime, if I use, I will try to use the same notations. You started with some vectors, U1, U2, U3, and you want to build the orthonormal 1, E1, E2, E3, E prime, E1, E prime 2, E1. Okay, D prime 2 would be defined by U2 minus orthogonal projection on the first one. Okay? Next one, you will take U3 minus the orthogonal projection on the first two vectors that you have made. Okay, so E prime 2 of x,
So x
x,
half of
half, yes,
I not half, but
of 1. Okay? That's, so E prime 2, this is this one, and you can check that it's really orthogonal to E1. Okay, what do we get? Indeed, do we have that integral of between 0 and 1 and x minus 1 over 2 times 1 dx? That's indeed equal to 0. Fine. Right? If you're not sure about your calculations, you can always check that it works. It's really orthogonal. What do we need to do next? We need to norm it. Okay, so we need to define E2 of x, which is x minus 1 over 2 divided by the norm of x minus 1 over 2. How do we get the norm of x minus 1 over 2? So that's going to be square root of the square root of the inner product of that the function with itself. Okay? And if you do that, I guess I can give you the result. You should get 1 over 2 square root of 3. If I'm not mistaken. But check that. Okay, so that's our norm version should be 2 square root of 3 times x minus 1 over 2. Okay? And then we're not going to do it, but you can build the next one. Next one out of x squared. It's going to be x squared minus the projection of x squared on E1 minus its projection on E2.
Well, you have to square the result of the integral and not what's inside it. Or is it the same result at the end? No. So why do we do this instead of squaring the result?
Squaring the result? No. What you're saying is that the integral of s squared is equal to the integral of s squared. That's not true.
Yeah, that's not true. So why do we write this instead of the other?
Because the norm of f squared of f is f.
Oh, okay.
Yeah. Okay, so that's that's equal to f inverse product with itself, which is defined by this. Right. So. Okay. Right. So I let you finish that, but I will let you finish that by yourself. Try it. Okay. Calculations are long, but that's a good way to do again some integrals. Right? So the third one, you build it out of x2 following the Gram-Schmidt process as usual. Okay? Same one as the one that works for all other kind of vectors. Okay? Right. And if you want to calculate the orthogonal projection of x3 on R2 of x, you use the orthonormal basis that we have built. Okay? So gather all your ideas. It's the same things as before. You will obtain an orthonormal basis in the end. So we've got already E1, E2. You make E3 out of X2. Okay? You take X2 and you subtract its projection on the first two ones. Okay, so you've got your orthonormal basis. And if you want to compute the orthogonal projection of something that is not in my space on my space, you just do as before. Okay, if you want to compute the projection on R2x of x3, what should we do? Yeah, as before. Inner product of x3 with E1 times E1 plus inner product of x3 times E2 times E2. Okay, that's the same definition of the orthogonal projection, as usual. Right? Except that E1 is my constant one function, E2 is x minus 1 over 2 multiplied by this 2 square root of 3, and the 3 is the one you can find by doing the third one in the process. Okay? All right, so we can go to the next one. So next one, again, spaces of function. So now we're in the space of continuous functions on 0, 5. Even to infinite with real values. We defined the same kind of inner product. Okay, that's, as I told you, it's one of the most common inner product when we talk for spaces of function. That's the other one. Right? And we defined a subspace of E, which is all the solutions, so all the functions that are continuous on 0 time, such that they solve the differential equation f second plus f is equal to 0. Show that f is a linear subspace, find an orthonormal basis, and find some projection on the orthonormal basis. Linear subspace, what should we do?
Linearity.
Yes, we have to prove linearity. Okay, that it's that any linear combination of items in F still belongs to F. Okay, so quickly, how should we do that? Linear space. Yes?
Zero element.
Sorry?
You need the zero element, then the lambda.
Okay. Do we have that 0 belongs to that space? Yes? Right? The 0 function? The 0 function, the one that for all x gives you 0. Okay? Second derivative of this function, 0. 0 plus 0 is equal to 0. Right? So 0 belongs to it. Then, next,
Lambda f1 plus
lambda f1 plus f2. Right? Assuming f1 is in f, f2 is in f, lambda is in O. Do we have that lambda f1 plus f2 belongs to it?
Of course. So we can expand that.
What?
We can expand using the f prime plus.
That's
f.
what we have to do. So, what is the characterization of things that belong to F? They solve the equation. Okay, that's how we characterize items in F. So, do we have that this linear combination solves this equation? That's right. Okay, so we plug the linear combination on the F1 plus F2 in the equation. And we want to show that it's equal to 0. Okay, it's going to come very, very easily, but we still have to write it. Okay, so what is the step that we need?
Need the linearity of the derivative.
Exactly. Second derivative. Well, first and second derivative is just a linear process, so that's going to be lambda f1 second plus f2 second plus lambda f1 plus f2. And then we rearrange in the part that concerns f1 and the part that concerns f2. Okay, so that's really, I can rewrite this as lambda f1 second plus f1 plus f2 second plus f2. Okay, just reorder the terms in that equation. And of course, as f1 and f2, they both belong to f, each of these is equal to 0. Okay? F1 satisfies the equation, F2 also, okay, as okay, so the linear combination satisfies this equation, so we really have linearity. Okay, so we've got a linear space. It's things that we did at the beginning of the semester. All right, so we've got a linear space. We have a well-defined linear product, so it's the same one as before. Same ideas. Symmetric, linear, bilinearity of the integral, and super bilinear, and then positive definite by positive definiteness of the integral. Okay, so we've got everything we need. And in that, we want to find a basis of f. So what can we do? Actually, so yeah.
You should just solve the differential equation.
Yeah.
And then we'll find the span of
Exactly. Yeah. So what are the solutions of this equation?
k exponential minus.
When I look at an equation, it's very rare that I can tell you what the solutions are. What should we do to find this? Characteristic equation. Okay? Characteristic equation. What do we get? Well, if I usually we use another variable than x most of the time, okay? Because x is either for functions or for variables. And it's really value, right? So usually I write it with these letters, whatever letters you want. We get r squared plus r plus 1, sorry. Right? If you've got an equation a y second plus b y prime plus c y is equal to 0, characteristic equation a r squared plus b r plus c. Okay, and you're looking for the roots of this equation. Roots of this equation.
Plus and minus 1.
Yep, so no real roots, we only have complex roots. So I agree with you can write it with the the complex exponentials, but when we want to stick only to real solutions, you know that you can rewrite the solutions. So in general, if you've got r is equal to a plus or minus I, sorry, alpha plus or minus I beta, you've got complex roots. Right? So the solutions are going to be exponential alpha t times arbitrary constant cosine beta t plus another arbitrary constant sine beta t. We will have time to do the chapter on differential equations again, right? So don't worry, we will work on that again, but that's just a quick reminder what you learned last year. Right, and we saw that quickly at the beginning, at the end of the semester. Right, so you've got plus and minus I, so it means that alpha is 0, the beta is 1. So in that case, we've got simple combination of cosines and sines. So all solutions are going to be written as so 1 constant times cosine plus another constant times the sine.
To the solution.
Okay? So, now, why is that giving me a basis? As you said. What have we found here?
That cosine sine is spanning
Yes?
basis.
Right. That I just need two functions, cosines and sine, in order to get all the solutions to the equation. All the items in my space are written as linear combinations of this. Right? So I can write this is equivalent, this line is equivalent to say that F, my space F, is spanned by the cosine function and the sine function. Okay, so I've got a spanning family for my vector space. If we wanted to show linear independence. I know that it's spanning. How could I show if I don't know yet about the scalar product? How can I show about linear independence? Yeah? We've got 2 items. I don't need recurrence here. When we've got 2 items, when are they linearly dependent?
When the constant makes 0. When the sum of them with the constant makes 0.
Okay, so in general, when you've got Q and V, how do you show that they are linearly dependent or not dependent? The definition, linear independence, if you've got lambda 1 U plus lambda 2 V is equal to 0, if you can find only solutions lambda 1 and lambda 2 equal to 0 to get that, means it's linearly independent. If you can find non-zero lambda 1, lambda 2, it means that they are dependent. When we've got 2 items, it's very simple to interpret this. It just means that if you can find non-zero lambda 1, lambda 2, it means you can write, for instance, this thing. So linear dependence when you have 2 items, it's just collinearity. Okay? 2 things are going to be linearly dependent if they are collinear. And they are going to be linearly independent if they are not collinear. Yes?
So why don't we have to prove it here?
Oh yes, you can prove it, but we're going to use the scalar product to prove something else, right? So yes, but if we just wanted to prove that it's a basis, you just need to prove that it's linearly independent, and obviously you can't find k such that cosine of x is equal to k times sinus of x. How can I show that I can't find one single value k such that this is true? What does it mean for 2 functions to be collinear? It just means that you can write one as a multiple of the other. Okay? Well, if I want to prove that it's not the case, it's very easy. I just take some specific values. Okay? So for instance, for x is equal to 0, I've got 1 is equal to 0. Never going to happen, whatever the case. Right? So I can't find. Right? So so that's impossible to solve. So they are linearly independent and they are spanning, so it's a basis. Right? Now, I know that I've got a basis. How do I make an orthonormal basis? Just like before. Okay? So what do we need to do? We take the first one. We just need to norm that. Yes?
In what you just erased, it depends on the value of x. I mean, what are the...
Okay. All right. Yes, good question. We want to show that they are not collinear. Right? If I want to solve this, not collinear, I'm going to write, I want to show that I can't write u is equal to k times u. Right? In my case, u is cosine of x, and v is sine of x. They are both functions. It means that they should be equal for all x. Can we find a value such that cosine of x is equal to k times sinus of x for every value of x? Okay? But even if but just the counterexample that I get, take x is equal to 0. You get 1 is equal to 0, that's never going to give you anything, any possibility, any constant. Right? If you take pi over 2, you would get 0 is equal to k times 1, so you could choose 1. Maybe k is equal to 0 works. Okay? But then if you take another value and keep k is equal to 0, cosine of x is not always equal to 0.
If we take, for example, p over 4.
Yes, but it's just for one value of x. Yeah, I want that the function is equal to constant times the other for all values of x. Okay? This is my vector. This is my vector. Okay, so that's going to happen. Okay, so very quickly.
Okay.
All right, so we should norm that. Right, what do we do to norm it? Well, that's what we do, right? But more interestingly, and so you get E1. Let's compute this one. Why do I do that? Because I know that in the Gram-Schmidt process, I should take, if I take E1 by norming that, my E2 is going to be the sinus of x minus this times the norm version of E1. Okay, so what is that? Yeah, there are many ways how you can see that. Or you can just say that it's sinus of 2x. Well, it's 1/2 sinus of 2x. Whatever. Or you can make u prime times u, whichever you want, okay? Okay, let's make it u prime times u. 1/2 u, so sinus of x squared. Between 0 and 5. What do we get? 0. Okay? So actually, they are already orthogonal. So to get your orthonormal basis, you just need to norm them. And you have an orthonormal basis. And then to make the projection, I guess there's a projection in the end, just as before. Use the scalar product. Okay? Okay. So, any questions?
Bon, bah, bon appétit.
Pirates. That's my pirates. First one, 0. What is the question? Rewrite it. That means that x plus 0, that 1 means that 5 plus 3. Okay. So this is that. I think it's x instead. And then I got
Bah non, parce que ça va pas dans le sac avec moi.
But so if you work on the result, it's very there. That's your hypothesis. It will be x and y, and the other side is going to be the z. Oh, but I know you can lessen your field, whatever. Try to work it in your head before trying to assess. Yeah. I have been integrating that.
Actually, but I know I just sur les figures.
So maybe you can change the way you work. So maybe think how you can change your way of working. Yeah.
just forgot to do it. So
Okay.
I was planning to do it after the micro.
Don't tell the others, but you can still do it.
Thank you very much.